And get started. Today, we're going to talk about what spectroscopy is. And our lectures over the course of the next couple of days will be on different types of spectroscopy. Today, we're going to be specifically talking about what IR spectroscopy is, and we're going to be talking about the locations for different functional groups on IR spectra. So first of all, what exactly is spectroscopy? Spectroscopy uses different forms of electromagnetic radiation, such as radio waves and ultraviolet light, and observes how these different frequencies interact with matter. And in this case, the matter is the solid product formed at the end of a reaction. So when you guys take organic chemistry lab sometime next year, you're going to be doing lots of different reactions, and oftentimes you'll end up with like this pale looking dust, and your TA will say, make sure you characterize your product. And what that means is you want to make sure that the product you have ended up with is the product that you were supposed to get based on the reaction. And IR spectroscopy is one way of characterizing the product. Different regions of the electromagnetic spectrum can give you different information when they're exposed to a compound. So again, with infrared spectroscopy, we're using specifically infrared light. We'll talk in a moment about some other types of spectroscopy and what types of electromagnetic radiation they specifically use. In all forms of spectroscopy, the process is similar. It generally involves shining the radiation through the solid sample and looking for different results as the light is transmitted and absorbed by the matter or by the product of the reaction. Alrighty, so here are a couple of types of spectroscopy that you will be discussing in 3570. The first one up here is mass spectroscopy, which uses fluorescent light. It measures the mass to charge ratio of ions. Next, we have HNMR and C13 NMR, which use radio waves, and they're used to identify molecular structure and the purity of a compound. Next, we have IR spectroscopy, which, as I have mentioned a couple times already, uses infrared light, and it is used to identify the presence of different functional groups, which can be pretty helpful because if you see, oh, my product in this reaction has these functional groups, and the product I was supposed to have also has these functional groups, that might indicate, okay, I did this reaction correctly. I have the product that I'm expecting to have. Alrighty, so more about IR spectroscopy. It uses infrared light and it's used to determine the different functional groups on a molecule, as I have mentioned a couple of times before, and it measures molecular vibrations as the infrared light is passed through the sample. And again, sample, compound, these are all used to refer to the product of a reaction. Now specify solid product of a reaction. The vibrations referred to are the bonds in the molecule stretching or bending. Absorptions can only be recorded if there's a change in the bond dipole moment due to the vibration. So the bond has to have a dipole moment, that is an electronegativity difference between the atoms. So for example, if I had a molecule like this, which is just Br2, I wouldn't be able to use infrared spectroscopy to determine whether there was some sort of vibration in this molecule because there's no dipole between these two atoms. They are both the exact same. You might hear this concept expressed as being a symmetrical molecule. For example, some professors might say you can't use IR spectroscopy on symmetrical molecules because if we look here, the molecule only has two atoms and it's like the same on both sides. It's just two BRs. So you've got to have a change in bond dipole moment or an asymmetrical bond to record an absorption of light in IR spectroscopy. Different functional groups absorb infrared light at different frequencies, and this allows you to use the recorded absorbances to track the functional groups of the molecule, determining its identity. All righty, and you can use this fact to determine which functional groups are present in a molecule. So this is an example of an IR spectra, and it's taken straight from David Klein's Organic Chemistry as a Second Language, second semester. I've referenced his book a lot, and I think it's just super helpful. And this is the second semester edition of the book. He has a first edition one and a second semester one. Wrote that up there in case anybody's interested, and of course, giving credit. You can see here that on the y-axis, we have the percent of infrared light that's transmitted to the compound, or the light that passed through the product and reached the little detector. And what's more important is these numbers down here, which are called wave numbers, not to be confused with wavelengths. We're going to talk a little bit more about wave numbers in a moment, but yeah, they're just down here on the x-axis. Now, there are two regions of the IR spectra that you should be familiar with. From about 1600 wave numbers to 400 wave numbers is called the fingerprint region. So about right like that. That is the fingerprint region. This is where bends in bonds are recorded. And generally, we don't use absorbances in this region when determining functional groups in 3570 because oftentimes it's really difficult to identify a particular region here, and it takes an expert to be able to interpret the data because it's different for each molecule. So that part's important. The data here is specific to the molecule, so don't worry about this part too much. However, you will want to pay a lot of attention to the characteristic region, which is 1600 wave numbers and up. In this region, characteristic. In this region, this is where absorbances due to bonds stretching are recorded. And this is where we normally look for functional groups because the different absorbances due to particular functional groups are the same for one molecule to the next. For example, if I have one molecule with an alcohol group on it and another molecule with an alcohol on it, I would expect a similar sort of indication in the characteristic region from one molecule to the next. So this is what we're going to be using both in OCSP and in 3570 and in Orgo Lab primarily. And I'm sure some of you might be wondering, how on earth are we going to be able to tell anything from this graph? Well, these sort of up and down lines, like you see how it goes down and then it goes back up, those form a peak, or they're considered a peak. And as I mentioned, different functional groups show up as the same type of peak consistently from one molecule to the next in the characteristic region. So we could use this fact and have some qualifying factors for each peak to help us match a particular pattern in the characteristic region to a particular functional group that might be present on multiple different molecules. And again, the way IR spectroscopy works, if you see a particular peak on the spectra, maybe you'll say, oh, this peak belongs to this particular functional group. And if the product you're expecting is supposed to have that functional group, then that indicates that you've performed the reaction correctly. Alrighty, let's talk a little bit more about wave numbers. The wave number is indicated by this signal right here. And the wave number is just the frequency of light over the speed of light. The units are 1 over cm minus, or I'm sorry, just 1 over cm, like that. And what's important to know is that wave numbers are directly proportional to frequency. So a wave number of 400 centimeters to the minus 1, this represents a greater frequency of light absorbed by the product than a wave number of 400 centimeters to the minus 1. And now I am going to pass it over to Sam. But before we do that, are there any questions on any of the material that we've talked about so far? It seems awful quiet, so I'll go ahead and quit screen sharing.
All right, thank you, Sydney. See if this works. There we go. Cool. So we're just going to go over a little bit of what Sydney talked about before and then get into some examples. So like we mentioned before, remember this is the same graph that Sydney was using a couple slides ago. The goal in looking at this IR spec, this crazy looking graph, is going to be essentially to determine the identity of different functional groups. And by doing so, either you can say, okay, I have these functional groups, I likely have the correct molecule, maybe if you're in Orgo lab, or maybe if you just know a bunch of the functional groups, you can determine what the structure of the molecule overall looks like. And so, like Sydney mentioned, we're going to use the absorbance peaks to help determine this. And so it's a little bit counterintuitive, but like Sydney mentioned, the peaks are actually going to be the pointy bits at the end. So they're not the top parts, they're the bottom parts. And so remember that the most important peaks, at least the ones we care about in this class, tend to be above 1600. I want to say that's 1600. So this entire thing is going to be the fingerprint region. And while you know this is useful for actual chemists, this is not useful for us. So we actually care about this region up here, the characteristic region. This is the one we like. And so now we're going to be talking about some of the important characteristics that we use to identify peaks. And so these in general are going to be the three: wave number, location, shape of the peak. I'll just write shape, and also intensity of the peak. And let me go through each of those real quick. Yeah, so like I mentioned earlier, different functional groups tend to consistently absorb at different frequencies of infrared light. So you can easily find these absorbances in Google. You'll see a lot of different cheat sheets. I'll show you one later. And one of these tables will be provided to you on the 3570 final. The professors tend to have like their own favorites that they like to give you. We'll also post some on the Canvas, and your study group leaders will walk you through how to do them. Essentially, what's going to happen is you're going to have like a table that lists common functional groups, maybe like amines, carbonyls, that kind of thing. And then from there, it shows you which wave numbers they tend to be at, maybe some of their characteristics. And from there, you can look at the spectrum and see if you have peaks that match up. And if you do, you can figure out what functional groups you might have. So let's say I had done maybe a reaction or an Orgo lab, and I'm expecting a molecule with a carboxylic acid. Probably going to look something like this. He looks kind of funky. But remember that you can characterize whatever product you got by doing an IR spec. That's something they'll show you in Orgo lab. And one of the functional groups we know, at least for this carboxylic acid group, is going to be this carbonyl, this C to O double bond. And I will go over this on the next slide as well. But let's say, for example, we know that the carbonyl, let me do this better, there we go, tends to have a big absorbance peak between 1600 and maybe like 1800 inverse centimeters. And so we can always look at our peak, or look at our IR spec and say, is there a peak at around 1600 to 1800 centimeters? And we're going to see, no, there's not really much happening here. So if, for example, I were expecting carboxylic acid, something with a carbonyl in my product, and I got this IR spec, I know I probably messed up somehow. And so while you don't necessarily have to memorize all these values, as I'm going to give you on the next page, it is like really helpful to be familiar with this kind of thing and at least be familiar with the tables that your professor gives you. It's going to help a lot when you do an on-it exam. So next up is going to be peak shape. So as you can see, the peaks on this IR look pretty different from one another. Some of them are going to be kind of narrow, some of them are going to be wider. So certain functional groups like alcohols are known for having more broad peaks. So let me write that down. OH, for example, is known for having smoother, broader peaks. They're also known for being, some sources will say like 2700 to 3200. I tend to see them around like a little bit above 3200, but we'll get into that. And then let's say we're also looking at our alkanes. Those tend to be a little bit spikier, especially the sp3 hybridized ones. Those tend to be below 3000. There's some nuance there. I'll show you what that looks like in a few slides. But let's continue our example from before. Let's say I'm a student in Chem 2510. Maybe I've just done a reaction. Maybe I want to figure out if I got the correct product. And so what I'm going to do is run this IR again, like we're talking about. Let's say our molecule has an alcohol group. Let's say it also maybe has a simple alkane. So the C to H, which is going to be sp3 hybridized. We talked about where you can find these, and then we can look at IR and decide, okay, do we see these two things? So we got these two big peaks on the left, hopefully you can see. So I'm going to circle that one in blue, circle the one to the right in red. And so you're going to see that the one in blue is going to be a little bit higher, also going to be pretty broad. It's not spiky like the one in red. And so even if, for example, we didn't know that alcohols tend to be on the higher side, so above 3200, we could say, okay, we know alcohols are supposed to be broad, so this is probably the alcohol. And the one, the red, is probably the simple alkane. And so, like we said, using the location of the peak based on its absorbance and also the shape of the peak, we can essentially determine that this is going to be the alcohol peak, this is going to be the CH peak. And so these two, I want to say peak shape and wave number location, in my personal opinion, tend to be the most helpful in determining what each peak is supposed to be. There is a third factor, however, and that's going to be intensity of the peak. And so something that we can notice about some of these peaks is that the intensity will differ a little bit. So essentially what this means, and the next graph will show it a little bit better, is that some of these peaks don't reach as far as the others. Now I know these are in the fingerprint region, but for example, you might see a C to C double bond tends to be around here. And these tend to be kind of shorter looking than say your carbonyls or your alcohols or your alkanes. And so intensity is associated with dipole moment a little bit. This isn't an exactly perfect association, in my opinion, at least. You're going to see that the intensity does tend to pan out for like some of these. So like, for example, your C to C double bonds, those are going to be way less intense than maybe your C to H's, C to double O's, your OH's, like I mentioned. But in general, I don't think intensity of the peak, while it is helpful for, doing this versus these guys, between these three where the intensity is all pretty, similar, not super helpful. And so now that we've done that, going to move on to this. So there are actually a ton of different kind of cheat sheets you can use. If you just Google, you're going to see a lot in terms of IR spec and determining what functional group goes where. So here's one we got from Master Organic Chemistry. This one I really like. Essentially, you're going to notice, like I mentioned before, a lot of differences in terms of location, wave number location, also the shape of the peaks. So, your alcohol is going to be very stretched here. A little bit of intensity. I don't think this graph is exactly perfect in showing it, but you'll see they showed the C to N's and the C to C's as being less intense. Alcohols here, I think they just put it up there, not because it's necessarily less intense, but just because they didn't want to overlap it. So like I mentioned, a good thing to do is when you have a chance, look on our website, see what table we have, see what table your professor uses, and also just look at different versions of these to get a feel for how different sources tend to classify these kinds of things. And so I'm just going to very quickly run you through some of the important points here. So remember, from about like 400 to 1600 is going to be your fingerprint region. Like we mentioned before, the fingerprint region, not super useful for us in this class. Next up is going to be 1650 to 1800. That's going to be your carbonyls, C to O double bond, 2100 to 2260 tends to be your C to N, C to triple C, your 2850, 2700 tends to be your C to H's for your aldehyde specifically. Right below 3000 tends to be your C to H's that are sp3 hybridized. Above 3000, your C. Another C to H. These are usually sp2 hybridized, but not necessarily aldehydes. Last but not least, 3200 to 3400 tends to be your alcohols. Remember, those guys are pretty broad. And so you may remember that I talked about the C to H as kind of having some nuance earlier. You're going to notice even in the master organic chemistry graph here, your C to H stretch can be pretty very wide range depending on what kind of C to H you have. So this is an instance where it's very important to know these tables really well and know the difference between is this an sp3 hybridized carbon I'm looking at? Is this an sp2? That kind of thing. And so also what I think is noteworthy here is you're going to see that these numbers for the most part agree with the master organic chemistry ones. You'll see other sources tend to use slightly different ones. So it's good to especially familiarize yourself with whatever your professor uses in addition to whatever your own study aids are. Without further ado, let me go ahead and copy paste this. We're going to get into some examples. I'm just going to put this little cheat sheet to the side there. And so generally, when you get an IR spec problem, it might look something like this, especially if you're doing a sapling problem. Essentially, they're going to give you your crazy looking graph. They're going to say, okay, what molecule could this represent potentially? So remember, first thing you want to do, ignore the fingerprint region. So down behind like 1600-ish, just ignore that. Next, what I like to do is I like to go ahead and circle my peaks where I see them. So I'm going to circle leftmost one in red, this in blue. Notice that these are actually two peaks. I'll talk about that a little bit later, but they're about the same intensity. Also, this one looks pretty promising. So now that we've looked at our peaks, let me go ahead and zoom in a little. This peak in red looks like, I would say around 3000. I like to go ahead and guesstimate kind of the position they are on the graph. The one in blue, I would say just below 3000. Notice that this is double peaks. So two peaks at approximately the same intensity, slightly different wave number locations, but very, very close. Last but not least, this yellow guy, I'm going to say maybe at 1750, it's my guess. And so now that we've done that, we want to go ahead and consult our handy dandy guide over here. So remember, for things above or at around 3000, we're going to say it's probably some form of C to H. So C to H. C to H sp3s, I think, tend to be the most common in this kind of example. We'll go ahead and leave it C to H if we're unsure. Just under 3000, we're going to see is your C to H's. Or sorry, yeah, your C to H's, but they're sp2 hybridized. And then over here, going to be your C to O double bonds. Again, following with what we said earlier, at C to O double bonds, the carbonyls tend to be around 1650 to 1800. And so given these things, we know, okay, between these two, maybe we have an aldehyde. Maybe we have something that looks like this. Aldehyde. We also have a bunch of C to H's. Since we already have sp2, we can probably say maybe these are sp3, but let's go ahead and look. So now that we know these things, there's going to be a carbonyl, there's going to be an aldehyde, there's going to be some other sp3 hybridized C to H's. Let's look at what we have. So we can go ahead and discount the first one, cyclobutanol, because that doesn't have an alcohol in here. Remember, we can discount anything else that doesn't have a carbonyl as well. There's another alcohol. So we've got these two left. This is where this example gets a little bit tricky. Remember that at the end here, at the ends will be methyls, whereas for 2-methylpropanol, there's just an H here. So 2-butanone, CH3, 2-methylpropanol, there's an H. So remember, because we decided we have an aldehyde, that we want an H right here, right? We don't want carbons on either side. So we're going to go ahead and discount 2-butanone and decide that 2-methylpropanol is our answer. Any questions on that?
Sorry, would you mind going over again how you found the aldehyde?
Yeah, so essentially what's happening is, remember, actually, would you mind walking me through what you would do in this example? Do you mind if I put you on the spot? You can say yes.
I'm sorry, like, what do you mean? Like,
yeah, so if you were given this example, let's say just this graph, what would be your process of walking through it?
well, I kind of wrote down as you were going a step process. So I guess, like you said, first ignore the finger region, which is why I was a little bit confused. Why the aldehyde is like written in.
Oh, I just wrote it on top of there because I didn't have room. I can move that if you want.
Oh, okay, got it. So then I guess the aldehyde region is between 2850 and 2780. And I guess that was like the double bond that you circled here in blue. Is that what you're referring to?
Yeah. So this is going to be, so aldehydes, C to H's. Remember that C to H stretch in the aldehyde is going to be sp2 hybridized. It's a little bit strange because you'll see that there's also sp2s that are sometimes above 3000. If we go back to this example, there's some sp2s that are here. There are also some aldehydes that tend to be lower. It is a little bit confusing. Essentially, what you want to look for with aldehydes is that they tend to have this double peak as well. So you'll see in some examples online, they'll almost call it like vampire fangs, something like that, something cute. But essentially, it's two peaks that are pretty close in intensity, and you can see, pretty close in wavelength as well. They're not like super far apart. And that will be characteristic of a C to H stretch, but specifically in an aldehyde. Does that make a little bit more sense? And so if you have this, and if you're not sure, for example, if you do have an aldehyde, remember that you should also be seeing a carbonyl. So you should have both these double peaks at somewhere below 3000. Like we said here, it's usually 2850 to 2700. But you should also have a carbonyl. If you don't have a carbonyl, then this is probably something else. It's not an aldehyde. Does that make sense?
Okay, thank you so much.
Yeah, of course. I think I saw another question. Yeah, somebody asked, sorry, is below 3000 sp3 or sp2? Yeah, so double peaks, like I just mentioned, I know this is a little bit confusing. The double peaks 2850 to 2700 is going to be aldehydes. That is an sp2, but remember there can be sp2s that are a little bit higher. So I'll show you in another example, but they tend to be a little bit higher than right at 3000. Like I mentioned before, that's another good reason to be acquainted with, not just this kind of cheat sheet from Master Organic Chemistry, but other ones online, but also like more specifically the one your professor gives you, because that's the one they're going to be basing their tests on. The C to H's tend to be a little bit tricky, If all else fails, what I like to do is go for like the kind of like the low hanging fruit, the ones like you probably know, like the carbonyls, the alcohols, that kind of thing. And then if all else fails, you can leave the CHs for the last. Also, most molecules tend to have like a bunch of CHs anyway. So sometimes it doesn't necessarily matter if you determine if something was, you know, sp2 hybridized versus sp3. Usually something like an alcohol or a carbonyl will be more important there. Yeah, hopefully that helped a little. Awesome. Any other questions there? I know this topic is super confusing when you first learn it. All right, I'm gonna keep going. Let's not take that whole thing with me. I don't care. There we go. All right, now to our next example. So same thing as before, ignore the fingerprint region. Let's look at our peaks. These are kind of short. I'm going to go ahead and discount them for now. If you're not sure, like I mentioned, go for the things that seem pretty obvious. So this big guy, this guy. Let's put this in blue. And also you'll note that sometimes they give you molecular formulas as well to help you out a little. I'm going to go ahead and let you know that right away, D, I believe, has 12 H's. So we're going to discount that. If memory serves, everything else follows this molecular formula. Obviously, that's a quick thing you can do at the beginning before you even look at the rest. So now that we've looked at our peaks and highlighted the ones we think are important, let's go look at them. So I'm just eyeballing this one, but I'm going to say it's around 3,400. And then this one is really just under 3,000. So we know if we have something around 3,400, generally the most important thing there is going to be an alcohol. You may see in your professor's table or other tables that they have other things up here. Generally, alcohol's pretty common in this type of problem. Remember that alcohols are also going to be very broad. This looks like, I think, a much more distinct U shape than, for example, the spiky guy down here. So we already know that we need an alcohol. So we can say no to that, no to that, no to that. And so this question ends up being not terrible just by virtue of, you know, us knowing that we have an alcohol, therefore only E can be the answer because D, once again, did not follow the molecular formula. Right under 3,000, if you're curious about this one, I would have said that that is an C to H, that's an sp3. And you'll notice here, lots of C to H's that are sp3 hybridized. Cool. So last but not least, it's going to be this one. Once again, same thing as always, ignore the stuff down here. You're actually going to notice sometimes there are peaks that are very close to the fingerprint region. So I want to say fingerprint region's about like here-ish, but there's this one that is just right outside the fingerprint region. I would go ahead and guess that it's maybe like right at 1650. And so when you see a big peak like this right outside the fingerprint region, you want to be aware of that. You don't want to just discount everything. Be a little bit vigilant because sometimes these will happen, although they are, in my opinion, like less common in these kinds of examples. There's some big peaks here. These look like, I would say there are both some below 3,000 and above 3,000. So remember, in cases where you don't have aldehydes, you may have C to H's that are sp2 hybridized above 3,000 and below 3,000. Those tend to be sp3 hybridized instead. Remember, if you're not sure if this would correspond to sp2 or sp3, you can see if there's a carbonyl. In this instance, we're not going to see anything that looks like a carbonyl, so we are probably good to go. And so the 1650 is a little bit rarer, but if we go ahead and look at, oh, my bad, I did not even write it here, but there is 1650s. Oh, you know what? Let me go back. Let me show you guys where it is. didn't show it here. That's not a good example. My bad. Anyway, let's add in another one real quick. At 1650, in addition to sometimes that carbonyl, you're going to have C to C double bonds. And so you might be thinking, okay, how do we know that was not carbonyl? One thing is that you can look at this, and if it's very, very close to one edge or the other, that tends to be a little bit iffy. It can in some instances be true. Remember, we also didn't see that sp2 aldehyde that tends to be a little bit lower than 3000 as well. So that is another hint without those double peaks. So that is another hint that we probably do not have that carbonyl, don't have that aldehyde. So now that we know those things, let's go ahead and look at these. So like we said, no carbonyl is gone. This is gone. This is gone. Also no alcohol. This is gone. Really no indication of like an oxygen at all, but if we want to be careful, we can say, okay, we see this C to C double bond. There's a C to C double bond here. This is probably the correct one. This is not. Any questions on that last one? Okay. If not, that is the end of this lecture. I know that this concept is pretty tricky, so if you have any questions for me, I'll be here for a few more minutes. If not, you're free to go.
Thank you.
Thank you.